Imagine, you've got this super advanced AI, like the most advanced AI ever made, and you ask it to prove Fermat's last theorem, the one that took mathematicians literally centuries to figure out. What do you think happens?
It probably just crashes, right?
Well, not quite. It doesn't crash. It just sits there,
Hmm.
stumped, just like its brain just freezes up.
Wow, really?
Huh.
That's kind of surprising. You'd think it could at least take a stab at it.
Right. You'd think with all the data and computing power it has, it could at least make some progress. But nope, it's totally lost.
So it seems like even with all the amazing things AI can do, there's still this barrier when it comes to higher level math.
Exactly. It's like it's hit a wall.
Yeah.
And that's where this whole idea of frontier math comes in.
Frontier math.
Yeah, it's this new benchmark designed to test AI against seriously hard math problems.
Well,
We're not talking about your high school algebra here. This is like graduate level mind-bending stuff. The kind of problems that would make even Fields medalists sweat a little.
oh, wow. So the real brain busters.
Yeah, exactly. And get this. The best AI models out there can only solve under 2% of these frontier math problems.
2%. That's it really puts things into perspective. I mean, we hear all the time about how AI is surpassing humans in so many areas, but it sounds like math is still a major challenge.
It definitely is. And there's this paper, FrontierMath, a benchmark for evaluating advanced mathematical reasoning in AI. It lays out exactly why they created this benchmark and what it's all about.
I'd love to hear more about that.
Well, the introduction in Section 1 talks about how the existing math benchmarks just aren't cutting it anymore.
What do you mean?
Well, AI has gotten so good at solving the problems in those older benchmarks that they're basically useless for measuring progress.
So it's like they've aced all the tests we have, and now we need to come up with harder ones.
Exactly.
Does that make sense?
The paper calls this saturation.
Saturation, huh?
Yeah, it's like AI has reached a saturation point where it can't really learn much more from those old problems.
So we need new, more challenging problems to really push the boundaries of what AI can do.
Absolutely.
Yeah.
But there's another issue, too. Contamination.
Contamination.
Yeah. The paper highlights how some AI models might have actually been trained on data that included those old benchmark problems.
So they're not really solving them, they're just remembering the answers they've seen before.
Right. It's like cheating on a test.
That's a
And that's one of the big things that Frontier Math tries to fix.
How so?
Well, for one thing, they came up with completely new problems that have never been published before. It's like a super secret exam that no AI has ever seen.
So it's a level playing field.
Yeah, exactly. And you can actually see how much of a difference this makes in Figure 2 of the paper. The unsolved rate for frontier math problems is over 98%, while it's way lower for those older, easier benchmarks.
98%. Wow, that's a huge difference. It really shows how much harder these frontier math problems are.
It definitely does. So I'm curious, what do you think about the people who came up with these problems?
I mean, they must be some pretty serious mathematicians.
Oh, yeah, they are. Section 2 of the paper talks about how they put together this team of over 60 mathematicians, from grad students all the way up to, like, super experienced professors.
Wow, that's a lot of brain power.
Yeah, and get this, a lot of them were math competition winners.
Math competition winners.
Yeah, like the kind of people who live and breathe math problems.
So they really know their stuff when it comes to tough challenges.
Exactly. And they didn't just throw any old math problem into frontier math.
So they had specific criteria.
Right. Section 2.1 lays out 4 key requirements for each problem.
4. Okay, I'm all ears.
All right. First up, originality. These problems couldn't be something you'd just find in a textbook. They had to be brand new, never seen before.
That makes sense.
Then there's automated verifiability. Basically, they had to make sure that a computer could check the answers.
Ah, so it's objective grading.
Exactly, though human bias or subjectivity involved.
Okay, what else?
Third, they had this thing called guess-proofness.
Guess-proofness.
Yeah, it's a mouthful. Basically, it means you can't just get lucky and guess the right answer. You have to actually work through the problem, use logic and reasoning.
So no throwing darts at a board and hoping for the best.
Right, you got to aim and shoot.
I like that analogy.
Okay. And the final requirement was computational tractability.
Computational what?
Tractability. It basically means that even though the solutions might be super complex, they can still be calculated by a computer in a reasonable amount of time.
Oh, right, so it's practical.
Exactly. It's like making sure the recipe isn't so complicated that you can't actually cook the dish.
That's a good way to put it.
So they came up with these problems, these really hard problems with all these specific requirements. But they didn't just stop there.
There's more.
Oh, yeah.
What else did they do?
Well, there was this whole review process, like a super rigorous review process.
Really?
Yes, section 2.3 of the paper goes into all the details. Each problem was peer-reviewed by other mathematicians. And they even ran them through plagiarism checkers, like QuedText and Copyscape.
Wow, they were not messing around.
They were serious about making sure these problems were top-notch.
It sounds like it.
And then on top of that, they even did a second round of blind reviews.
Blind reviews.
Yeah, just to try and figure out their error rate.
Interesting.
And they found it to be around 10%.
10%, that's actually pretty impressive, especially considering how subjective math problem difficulty can be, right? What seems impossible to one person might be a breeze for someone else.
That's a great point, and that's something they really acknowledge in section 2.5 of the paper. They even developed this fascinating system to assess problem difficulty. They call it a three-dimensional rating system.
Three-dimensional.
Yeah, so it's not just easy or hard, it's more nuanced than that.
So how does it work?
Well, think of it like a map of how hard a problem is.
Okay, I can visualize that.
One dimension is background. Like, what level of knowledge do you need to even understand the problem?
That makes sense.
Another dimension is creativity, as in, how many light bulb moments will it take to solve this thing?
Right.
And the third dimension is execution. How much actual work, how many calculations and steps do you need to go through to get to the solution?
Okay, so they're trying to capture all the different ways a problem can be challenging.
Exactly.
But like you said, judging difficulty can be tricky. How do they know this system actually works?
Well, they've been collecting data on how well AI models perform on problems with different difficulty ratings.
Yeah.
And even though it's early days, the results are looking pretty good.
What do you mean?
They're finding a correlation between their difficulty ratings and how well the AI actually does on the problems.
Interesting.
So it seems like they're onto something.
It does.
Okay, so we've got these incredibly hard math problems. But how does frontier math actually work in practice? The AI doesn't get a pencil and paper, right?
Right, I was wondering about that.
Yeah, it's a bit more high-tech than that. Section 4.1 of the paper describes this really cool experiment-enabled framework they've set up.
Experiment enabled.
Yeah, basically the AI model can write and run Python code to test out its ideas, just like a human mathematician might.
Wait, so the AI is coding?
Yeah, it's running its own little math lab, playing around with code to see what works.
That's amazing.
It's a really dynamic process. The AI analyzes the problem, tries to come up with solutions, writes code to test those solutions, gets feedback from the system, and then refines its approach.
So it's not just passively crunching numbers, it's actively experimenting.
Exactly. And just like any good scientist, the AI has to present its final answer in a very specific format. This is all explained in section 4.1. They have strict rules about using Python scripts, pickle files, and wrote detailed comments.
So everything is transparent and verifiable.
Right. Now, are you ready for the big reveal? How did the AI actually do on these crazy hard problems?
Yeah, I'm on the edge of my seat.
Well, the results are in section 4.2.1, and drumroll please, even the best AI models could only solve less than 2% of the problems.
2%. Ouch, it sounds like these problems really put AI through the ringer.
They definitely did. But maybe that's the point, right? To show us where AI's limits are and push it to get better.
Yeah, I think that's a good way to look at it.
And the paper actually dives into how different models approach the challenges in section 4.2.2. Some were quick to guess, like they were just trying to throw something at the wall and see if it stuck. Others were more methodical, taking their time and running experiments.
So it's like they have different personalities.
It really is. It's fascinating to see those differences.
It makes you wonder what's really going on inside those AI minds.
For sure. Now, section 5 of the paper does a great job of putting all of this into context. It explains how frontier math fits into the bigger picture of math reasoning evaluation.
Oh, that's helpful.
Yeah, it goes through how things have evolved from those simpler data sets to these more challenging benchmarks. And it highlights how important it is to avoid contamination, like we talked about before.
Right, to make sure the results are meaningful.
Exactly. It's clear that frontier math is a big step forward in how we measure AI's ability to do math. Now, I heard they even talked to some big-name mathematicians about all of this.
Oh, that's interesting.
Yeah, section 6 of the paper highlights some interviews they did with these prominent mathematicians. We're talking about like the rock stars of the math world.
Cool.
And you know what? They were all in agreement that frontier math problems are seriously hard.
Even for them.
Even for them.
Wow, that's saying something.
And they were pretty skeptical that AI could solve these problems anytime soon, at least not without a lot of help from humans.
So they're not too worried about being replaced by robots just yet.
Not quite. They seem to think that human-AI collaboration is a more realistic goal.
Like a team effort.
Exactly. They also pointed out that one of the biggest hurdles is that there isn't enough data out there for AI to learn from, especially when it comes to these really specialized research topics.
It's like trying to learn a new language without any textbooks or native speakers.
Exactly. But they also talked about some really interesting ways that a frontier math-capable AI could be helpful. Things like assisting with complex calculations, testing out new theories, and handling all the tedious tasks that mathematicians have to do.
Kind of like a superpowered research assistant.
That's a great way to put it.
It's exciting to think about the potential there.
It definitely is. Now, before we get into the specific problems themselves, let's talk about the different types of math covered in frontier math.
Sounds good.
Section 3 of the paper describes the composition of the dataset, and it's really impressive. Frontier math problems cover a huge range of mathematical topics, everything from number theory and combinatorics to abstract algebra and even some theoretical computer science.
Wow, it's like a smorgasbord of math.
It really is. And it's not just a random assortment of problems either.
So there's a structure to it.
Right. They wanted to capture the interconnectedness of different areas of math. Figure 4 actually shows this beautifully with a network visualization. You can see how different mathematical subjects are clustered together, reflecting how mathematicians often pull from different areas to solve problems.
So it's like a map of the math universe showing how everything is connected.
Exactly. And it shows how frontier math isn't just about testing AI's knowledge in one specific area. It's about testing its ability to connect ideas, see the bigger picture, and solve problems creatively.
That's a much more holistic and realistic test of mathematical thinking.
Absolutely. Now, if you want to get a real sense of what these problems are like, we need to dive into Appendix A.
Okay, let's do it.
It's like a treasure chest of mathematical puzzles, each with its own challenges and surprises.
I'm intrigued.
The appendix showcases 5 sample problems with different levels of difficulty. You can see them summarized in Figure 7. We have problems from different mathematical fields, each requiring a unique set of tools and techniques to solve.
It's a great way to get a taste of what frontier math is all about.
And the best part is, they don't just give you the problem, they walk you through the solution step by step, explaining the logic and calculations behind each step.
So it's like having a master class in advanced mathematics.
Exactly.
It's worth noting, though, that even the low difficulty problems are still pretty challenging.
Oh yeah, they're definitely not your typical homework assignments.
Agreed.
Okay, let's start with the hardest one. Problem 1 in Section A, Boot 1. It's called Testing Artin's Primitive Root Conjecture. And let me tell you, this one is a doozy.
A doozy.
Yeah, it involves some seriously advanced number theory.
Okay, I'm ready.
It takes you deep into the world of prime numbers and how they behave. Specifically, it focuses on this idea called a primitive root.
Interesting.
And the solution they provide is super detailed. It walks you through the entire thought process, including references to research papers and concepts like the Chebotarev density theorem and the generalized Riemann hypothesis.
Wow, that's getting pretty deep.
It is. And to really show how complex this problem is, they even provide a link to a C++ script on GitHub that helps calculate the answer.
A C++ script.
Yeah, it's like they're saying, hey, if you don't believe us, try it yourself.
That's a serious challenge.
It is. Okay, let's move on to Problem 2 in Section A.2, the high-medium difficulty problem. This one is called Find the Degree 19 Polynomial.
Okay. A bit less intimidating than the last one, maybe?
Maybe. This problem brings in ideas from algebraic geometry and group theory. You're asked to build a polynomial with specific properties that make a curve with a certain number of irreducible components.
Sounds complicated.
It is. And the solution takes you on a wild ride through concepts like monodromy, branch loci, and the Riemann existence theorem.
Wow, that's a mouthful.
It's like a crash course in some of the most mind-bending areas of math.
It's a great example of how these frontier math problems often require you to combine knowledge from different areas of math.
Exactly. It's not enough to just be a specialist in one field. You have to be able to make connections and see the bigger picture.
I see that.
All right, let's shift gears a bit and look at Problem 3. The medium difficulty problem in Section A.3. This one is called Prime Field Continuous Extensions.
Prime field continuous what?
Extensions.
Oh, okay.
This problem dives into the world of p-adic analysis and recurrence relations. The goal is to find a prime number that has a specific property related to how a sequence, defined by a recurrence relation, continuously extends.
That's a lot to unpack.
It is. The solution involves something called the Skolem-Mahler-Leak theorem, and this idea of p-adic valuations.
I'm not even going to try to pronounce those.
Fair enough. But it's a great example of how frontier math can introduce you to all these new mathematical ideas and tools.
Even if you don't solve the problem, you're still learning something.
Exactly.
That's cool.
And even though it's classified as medium difficulty, it's still pretty challenging. You need a solid grasp of abstract algebra and number theory to even begin to wrap your head around it.
So it's not a walk in the park.
Definitely not. Okay, let's move on to problem 4, the medium-low difficulty problem in section 8.4. This one is all about matrices and group actions, and it's called Find the Number of Orbits.
Matrices and group actions. Okay, that takes me back to my college days.
It asks you to figure out the number of orbits of a particular group action on a set of 4 tuples of matrices.
Right.
And the solution they provide is really clever. It connects the problem to the representation theory of the symmetric group and uses its character table to figure out the possible representations.
I'm starting to see a pattern here. These problems really test your ability to think outside the box and apply different areas of math.
Absolutely.
Yeah.
And remember, it's not just about finding a solution. It's about proving that your solution is correct.
So there's a lot of logical reasoning involved.
Yeah, it's about understanding why the answer is right, not just getting the right answer.
Makes sense.
Okay, and finally, let's look at the low difficulty problem. Problem 5 in section 8.5, titled, How Many Non-Zero Points?
Low difficulty, huh? We'll see about that.
It's the most accessible of the 5, but it's still no cakewalk.
I bet.
It's all about counting the number of solutions to a polynomial equation over a finite field.
Okay, I can picture that.
And the solution they present is really elegant. They use a Python script to count the solutions for smaller fields, and then use the Hasselbalch bound to get a limit on the number of solutions for a bigger field.
So it's a mix of computation and theoretical results.
Exactly.
Very cool.
Wow, we've only scratched the surface of these sample problems.
Yeah.
But they give you a real sense of how diverse, challenging, and thought-provoking frontier math is.
It's like they've given us a glimpse into the future of math research and the potential role AI could play in it. It's pretty exciting.
It really is. Now, in part 2, we'll dive even deeper into the details of how these experiments were run and what the results tell us about the current state of AI. We'll also explore the philosophical implications of frontier math and what it means for our understanding of intelligence. So stay tuned.
It's really amazing what they've done with frontier math. Appendix B takes us even deeper, giving us a look at how they actually ran those AI experiments.
Oh, cool. It's like we get to peek behind the curtain and see how the sausage is made.
Exactly. Section B.1 is especially interesting. It shows the actual prompts they use to guide the AI models.
So these aren't just humans sitting down with a pencil and paper.
No, not at all. We're talking about language models interacting with a system that's specifically designed to challenge them.
I see. So what do these prompts look like?
Well, first, there's an initial prompt that kind of sets the stage. It introduces the problem and explains how the AI can use Python code to experiment and test out its ideas.
Okay, so it's like giving the AI the instructions and tools it needs to get started.
Exactly. Then there are continuation prompts that provide feedback after each interaction with the system.
I see.
These prompts are designed to kind of nudge the AI in the right direction.
Like a coach giving you tips.
Exactly.
Yeah.
And they also emphasize the importance of using code to double-check reasoning.
To make sure the AI isn't just jumping to conclusion.
Right. And speaking of staying on track, they're very specific about how the AI needs to present its final answer.
So it's not enough to just spit out a number.
Nope. There's a whole protocol involving Python scripts, pickle files, and very carefully written comments.
So it's all about making sure everything is clear, consistent, and verifiable.
Precisely. Those are all essential for any good scientific benchmark.
It sounds like frontier math takes those things seriously.
They definitely do.
Now, what happens if the AI gets stuck? Or runs out of time before it finds a solution?
That's where the final prompt comes in. It encourages the AI to give its best answer, even if it's not totally sure.
So it's like saying, okay, time's up. Show us what you've got.
Yeah, pretty much.
So they really thought of everything.
They really did.
It's impressive how much care and effort went into creating this evaluation framework. It seems like they wanted to give the AI models every chance to succeed, while still making sure the problems stayed super challenging.
I agree.
So how did the different AI models actually approach these challenges?
Well, section B.2 of the paper dives into that. Remember, we're not just looking at whether the AI got the answer right or wrong. We want to understand how it thinks, what its strengths and weaknesses are.
It's like trying to understand the personality of an AI.
Right. And Table 2 gets to the heart of this. It shows the success rates of different language models, not just over one attempt, but over multiple runs on 4 specific problems.
And what's interesting about that?
Well, what stands out is how much the performance varies, not just between different models, but even within the same model on different
Oh,
attempts.
there's an element of chance involved.
It seems like it. It's like rolling the dice, but the dice are incredibly complex, and the rules of the game are constantly changing.
That makes it even harder to analyze what's going on.
It
It
does.
makes you realize just how much we still don't know about AI.
Absolutely.
Now, speaking of comparisons, Section B.3 looks at how frontier math stacks up against those older math benchmarks we talked about earlier.
Right, I was wondering about that.
Figure 2 does a great job of showing this visually. It presents a whole spectrum of benchmarks, starting with relatively easy ones like GSM 8K, where AI is now getting almost perfect scores.
Right.
Then you have tougher ones like AIM and OmniMath, where the success rates drop significantly,
And then there's frontier math, way out on the edge.
with that unsolved rate of over 98%.
It's a real reality check.
It definitely shows how much harder frontier math is compared to anything else out there.
No doubt.
Now, throughout this whole conversation, we've been talking about problem difficulty. But how exactly is difficulty measured in frontier math?
That's a great question. And Appendix C gives us a look at their process for assigning those difficulty ratings.
Okay, because it can't just be a matter of saying, this one feels hard, so it's a 10.
Exactly. They acknowledge that judging the difficulty of math problems can be subjective. What's super hard for one person might be a piece of cake for another.
Right, right.
But they've created a system that aims to be as objective and consistent as possible.
So how does it work?
Well, they use that three-dimensional rating system we talked about earlier. Background, creativity, and execution.
Right, to capture the different ways a problem can be challenging.
Exactly.
And then, to make sure their system is actually working, they've been collecting data on how different AI models perform on problems with different difficulty ratings.
So they're constantly testing and refining their system.
Precisely.
And the good news is that the early results look promising.
That's good to hear.
It seems like their difficulty ratings actually do line up with how well the AI models perform.
So it's not perfect, but it's a step in the right direction.
Definitely.
And it's not just about the difficulty ratings. Frontier Math also collects a ton of other information about each problem.
Oh, really?
Yeah, Appendix D lays all of this out.
What kind of information?
Well, Table 3 lists all these different metadata tags they use,
Yeah.
and it explains what each one means.
Okay.
We have background ratings, creativity and execution ratings, lists of subjects and techniques, and even tags that tell you whether you need to write code to solve the problem.
Wow, they really went all out.
They did. It really highlights their commitment to making frontier math a valuable resource for anyone interested in pushing the boundaries of mathematical reasoning.
I agree.
It's clear that frontier math is more than just a benchmark.
It's a testament to the power of collaboration between mathematicians and AI researchers.
Absolutely. And by working together,
Yeah.
they're not just testing the limits of AI. They're pushing our own understanding of what it means to think mathematically.
That's a great point.
Now, before we wrap up, let's talk about the bigger picture. What does all of this mean beyond just solving math problems?
Yeah, that's the big question, isn't it? Like, what does all this mean for the average person?
Right, because not everyone is going to be proving theorems or writing AI code.
Exactly. But what's so fascinating about frontier math is that it's not just about math or AI. It's really about understanding what intelligence is, you know?
So I like that.
The discussion section of the paper, section 7, kind of touches on this. By setting such a high bar for AI, it forces us to ask, what does it even mean for AI to solve a math problem? Is it doing it the same way a human would?
Right, because we think of math as this very human thing.
And it makes you wonder, are there fundamental limits to what AI can do in math? Or is it just a matter of time before it surpasses us?
That's a question that keeps coming up in AI, right? Like, how
Energy.
far can it really go?
Totally. And the paper presents some interesting perspectives from those interviews they did with the mathematicians. Remember, these are some of the top minds in the field. And they were all pretty impressed with how challenging the frontier math problems were.
Yeah, but they weren't exactly panicking about losing their jobs to robots, were they?
No, not really. They actually seemed cautiously optimistic about the potential for AI to contribute to math research. But they emphasized that collaboration between humans and AI is key.
So it's not about AI replacing mathematicians. It's about AI helping mathematicians do even better work.
Right. It's like a partnership where each brings their own strengths to the table.
And one of the things they pointed out is that even if AI can solve a math problem,
It doesn't mean it understands the concepts the same way a human does.
It's like the difference between knowing the answer and knowing why the answer is right.
Exactly. And even more than that, it's about knowing how to ask the right questions in the first place,
And those are the skills that still seem to be uniquely human.
at least for now.
It's really amazing to think that frontier math is doing more than just testing AI. It's pushing us to think differently about what intelligence is and what it could become.
And that's what makes it so exciting. The journey is just beginning. Section 8 talks about how they're planning to add new problems, experiment with different evaluation methods, and keep pushing the boundaries of what's possible.
It sounds like frontier math will be a valuable resource for a long time to come.
I think so.
It's an exciting time to be following this field.
It really is.
Well, that's it for this deep dive into frontier math. We hope you enjoyed exploring this fascinating world with us. Until next time, keep asking questions, keep learning, and keep pushing the boundaries of what you think is possible.